Swayam Prabha. Digital India. Educated India.
So, we started this, we went on this journey because we were talking of optimization with inequality constraints. And the first kind of problem in that, the first kind of the simplest sort of, you can say, problem of optimization with inequality constraints is when you are minimizing a linear function over linear inequality constraints. So, minimizing C transpose x, where the x is your variable subject to the constraint that A x is less than equal to B. Okay. So, what are you doing here? You have your objective now is a linear function. The constraints are, what are the constraints? The constraints are linear inequalities. What do, it's a common region that lies in all of these inequalities. Linear, so it's a common region of all of these half spaces. So, the feasible region is a polyhedron, right. So, we are optimizing a linear function over a polyhedron, and so that is what is called a linear optimization or a linear program. A linear program is, so you have a linear objective, the polyhedral feasible region. Okay. So, this sort of problem is what is called a linear program. So, let us look at what let us try to see what we can say about solutions of a linear program. Okay. So, firstly, the way this problem has been posed, we are optimizing a linear function over a polyhedral region, okay, a polyhedral feasible region. Can you show me how this problem can be transformed into a problem that looks like this? So, how do I transform it from this to this? Does everyone understand what it means to transform? So, we would like to take this a problem like this and do some transformations that we had discussed earlier, introduce variables, change type of constraints, etc. Do whatever transformation you can to bring it to this sort of form. When I say this form, I do not necessarily mean that I am only concerned about the form of the problem. Means this A here doesn't have to be the same A here. Similarly, this B and this B doesn't have to be the same. This C doesn't have to be the same. In fact, this X and this X also doesn't have to be the same, right? But I should be able to recover the solution of one from the other. Okay. So, can you tell me how do I do this transformation? Okay. So, the first thing is which we have seen was the introduction of slack variables that lets you convert inequality constraints into equality constraints, right. So, the first let's try to do this. So, first, so introduce a slack variable s, and that then gives you this equivalent optimization. You are minimizing C transpose x over the constraint now A x plus s equals b, s is greater than equal to 0, and now your object the variables over which you are optimizing is both x and s. Okay. So, now is this problem, question now is this problem in the form of this problem? What is the difference in the form of these two problems? Right. So, the key difference is that here only the if here remember what is the role of x in this on the problem on the left hand side. The role of x here is that of the decision variable. So, it is representing all the decision variables together. All of them are required to be greater than equal to 0 in this problem. Whereas, if you look at it on the if you look at the problem on the right hand side, the decision variables now comprise of both x and s. It is these together, but the problem only has some of them greater than equal to 0, which is the s component of it is greater than equal to 0. The rest are not, we are not imposing greater than equal to 0 there, right. So, this is not in the same form as this, right. The problem on the left hand side has the form where all decision variables are greater than equal to 0, the right hand side has only some of them. So, we have to somehow do more work to get it to this form. Remember, focus is on form. Of course, x itself you cannot ask for x suddenly to be greater than equal to 0, because it may not be valid in this particular problem. So, you have to transform x into some other using some other variables in such a way that you get it to this sort of, those variables end up having this sort of form. So, what would be the way to do that? So, one simple way of observing this is, notice that x is is a real vector. It can take any both it can have positive as well as negative components. Take any component of x, then that is just a real number. It can be positive or negative or 0, but every real number can be written as a difference of two positive numbers, right, always. So, component wise I can always write x as the difference of two non-negative vectors, right. So, I can do this change of variables. I can replace x by u minus v, where u and v are both non-negative. Since u and v are non-negative, the difference, but I am looking at the difference. The difference can take both positive values, negative values, can take 0 also. Every possible value of x can be generated as a difference u minus v, where u and v are non-negative. So, if I make this transformation, this will not change this transformation is going to be equivalent. So, I can make this change, instead minimizing C transpose x now becomes minimizing, my x gets replaced now by u minus v, a is going to be multiplied by u minus v plus s equals b, but I am going to keep u and v non-negative. So, I will have inequalities s greater than equal to 0, u greater than equal to 0, v greater than equal to 0. Now, what are my variables now? The decision variables of my optimization, s, which is earlier, remains, and in addition to that I have u and v also. So, I am now optimizing over u, v and s, right. So, I can just write this whole thing in a neater form. me write it like this, minimizing over u v s, this sort of function where c minus c 0 u v s Now, question is this in the form of this problem on the problem that I was looking for? Yes, it is in this form because all my variables are now non-negative. I have equality constraints, or the other constraints are all equality constraints, and I have a linear objective. Right, but you see in the process of getting to this form, my x has completely disappeared. Right. So, when you are changing the form of the problem, you should be open to changing, redefining your variables, redefining your constraints, introducing new variables, etc. Right. So, but focus should be on the form, not on retaining the identity of particular variables. Right. So, what it means is that what the conclusion from this is that if I give you any linear program like this, which is optimizing a linear function over a polyhedron, after some transformations, I can bring it down to this sort of form. Now, can you tell me if you can make this even more specific? So, I have brought the a linear optimization problem to this form. Can you make it even more specific? Say more about, remember the transformations we had discussed. We had discussed things like eliminating constraints, for example. So, are there some constraints that you can trivially eliminate from here? So, look at, we have linear equality constraints here. So, if there are rows of A that are linear combinations of some other rows of A, right, then it has to be that then you can eliminate those. So, if there is a row of A here, so look at the matrix A, there is some row here that happens to be a linear combination of these two other rows, and you have B on the right hand side here, the corresponding B. Here is your B, this is B, this is A. Now, when I do row transformations, I can, by using row transformations, I can basically make all of these 0. When I am doing row transformations, what am I doing? I am multiplying this row by the rows by some constants, adding them to other rows, and subtracting them from other rows, etc. Right. So, by doing that, I end up eliminating make this entire row 0. So, it is as good as not present. What should happen to this after those transformations? If these equations are consistent, this should also become 0. Right. Otherwise, these equations are not consistent, in which case there is the feasible region itself is empty. Right. So, if this with this and this with this and the original form of these 3 equations, if they are consistent, then after these rows transformations, not only should this disappear, this should also become 0. Right. So, in short, that entire constraint should become irrelevant. Right. So, if the feasible region is non-empty, then without loss of generality, I can do these transformations and get rid of all these linearly dependent additional constraints. Now, is this changing the geometry of the problem? Is it changing the feasible region? It is changing the number of constraints, but it is not changing the feasible region. right, because the feasible region is the set of x's that satisfy these constraints, and the same x's that satisfied your earlier set of constraints continue to satisfy the reduced set of constraints also, because you have only removed the some linearly dependent constraints, correct. So, the feasible region does not change, but constraints get removed. No, x, the dimension of x remains the same, it is only the number of constraints which is changing, right. So, remember, feasible region is a region in space, constraints are just an algebraic way of representing them. There are many redundant ways by which you can represent the same region, and we are removing all this redundancy by getting rid of these dependent equations, right. Okay. So if the problem is feasible, then I can do the above transformation, then by row transformations we can reduce the problem to this form. We get something like this. You are minimizing a linear objective C transpose x, again over the form of the constraints is still the same, A x is equal to B, x is greater than equal to 0, form of the constraints is still the same, but what can we say? I can now say that if I look at the rank of A, that is then that has to be equal to the number of rows of A. So, A is full row rank. Clear? So, by doing, so this is another further reduction. So, I had a general problem like this where I had an equality constraint A x equal to B and x is greater than equal to 0. I have now said, well, that also I can be more specific. I can take A to be full row rank. Can you be even more specific then? Is there any further reduction possible? This A is no more the same A that you started with. The A we started with is this. The A we ended up with is this sort of A, and this may have linearly dependent rows. So, question is that I asked was, is it possible to make this problem even more specific? Can you say something more? Sorry, no, x is greater than equal to 0. That's just a constraint. Yeah. So, we can make them more specific, make it more specific by to the point where we now begin to solve the problem. Okay. So, but that is not what we are trying to do. We still want to we do not want to dive deep and begin solving the problem, but we want to still looking at the form itself try to be more specific about it. So, instead of an arbitrary A, now we have an A which is full row rank. What about B? In all these transformations, B has actually been left untouched. So, B can actually be taken as greater than equal to 0, and this is without loss of generality. Can you tell me why? So, without loss of generality, B can be taken as greater than equal to 0. So, if I try to do what you are saying, which is that I write B as B1 minus B2, take the one of the as a difference of two non-negative B's, you will take one of them to the left hand side, but it is not being multiplied by x. Yeah. So, the point here is it's a very simple observation actually, that here you have equality constraint. So, they remain valid even if I multiply any one of the rows by minus 1. So, if I have a B which is negative, I can just multiply that particular row throughout by minus 1. The corresponding row of A will get multiplied by minus 1, the corresponding B gets multiplied by minus 1, and I get back on positive B, right. So, by doing this I can get without loss of generality I can assume B to be greater than equal to 0, right. So, what this means is, so this gives us the final form that you can do minimize C transpose X, Ax equal to B, X greater than equal to 0, B greater than equal to 0, A full row rank. This is what is called the standard form. Standard form of a linear program. Now, why care? Why do all this? The reason is because once you have a standard form, standardization like this helps in creation of technology on top of it, right. Once you have a standard form, you can people can create methods for solving that particular problem of that particular form. If you have too many different forms, then there is no fixed form, don't know which one to choose and so on, right. So, you will see that many solvers usually assume that you are starting off your linear program in the standard form. So, they demand that you enter your problem in a standard form, right. Okay. Of course, there you can anything that's written in this sort of form is at the end of the day a special case of the first definition that I mentioned. It is eventually a linear optimization of a linear objective over a polyhedral feasible unit. So, if the solver demands that you write it in this form, you can also write it in this form clearly, right. Okay. So, we will end here and we will continue next time.